Okay, so in this video we will look at the table, Laplace transform table. So we have looked at before in the previous video that we can perform Laplace transformation by employing this equation, the general equation for Laplace transformation, which is if we have a signal in time domain, which is in this case ft, right? If we have ft, a signal in time domain, then we can transform this into the frequency domain by using this equation, right? So next we'll see how we can directly perform the Laplace transformation by just using the table. So here we have Laplace transformation pairs table. Okay, so you can see here the some of the transformation which we have seen in the previous video has been included in this table. For example, previous video, in one of the example, you can see that for 1 ut, right, we use the equation to get the fs, we will get 1 over s, right? And also in one of the examples we see that if we have function ft of exponential negative at, right, we perform the Laplace transformation using the equation, we can get 1 over s plus a, right? Same thing for sine omega t and then cos omega t. Alright, so basically this is the summary simplification, right? So we have done all this, and this is the Laplace transformation of each of these ft, right? And take note that this is true. Okay, you can apply this table only for t0 and above. All right. So ft is 0 for t below 0. Right. So this is only apply for unilateral mode. All right. One direction. Okay, not two direction. All right. And then besides the that table, okay, we also have this table properties of Laplace transform. So you can see these are the properties where you can apply when you do the Laplace transformation. For example, if we have a function, right? For example, we have a function which is a combination f1 plus f2, right? So you can perform the Laplace transformation using the table and referring to these properties as well. So if the function ft is in this form or in this format, you can simply transform the function in this form. Alright, and if the function is in this form, then the transformation is simply referring to this form. Okay, we will look at how we can apply this in a few examples after this. Right, so same thing, this is basically the same property table, right? Okay, so we have linearity. Let's see what we can alright, so if you can see here, if we have a function of first ft and then function of second ft, first function and second function, and we have addition between these two functions, right? So to do the Laplace transformation, we can just simply perform Laplace transformation on each of these signal individually, right? As long as they are both connected by addition or subtraction, right? So this is what it means by linearity, right? Basic theorems for the Laplace transform scaling. Okay, scaling. Example of scaling. Sorry. Example of scaling. So, let's say we have a function, okay, and the time is multiplied by a, right? So the Laplace transformation for that is 1 over a, Laplace transformation of the function itself, and the s is divided by a. Alright, let's look at one example here. Okay, so we know that sine omega t ut, right, the function here, and if we refer this to the Laplace transform table, right, simply by referring to the table, we can get that the Laplace transform is omega over s squared plus omega squared. Right, this is directly taken from the table. However, if we have sine 2 omega t ut, alright, so in this case, this is the f2t, right? So in this case, we have this as the at, right? This is the a. So now, if we referring to this table, right, to perform the Laplace transformation, this 1 over a is 1 over 2, which is this. This is the a, right? And then, so this 1 over 2 is this 1 over a. And then once we have that, we need to do this fs over a. So what is Laplace transformation of this sin omega t, which is this, right? Right, which is this s squared omega squared. But take note that for every s, we have to divide it with a. So every s we need to divide it with 2. In this case 2. Right? This is the a. Right? So once we do this, so the answer is this. Right? That's the idea of scaling. Okay, the properties of scaling. Next, let's look at the properties of time shift. So here, if we have a function that is the time subtract by a or minus by a, or shift, alright, the time shift by minus a, and then the ut itself also must be shift by a, then we can get the Laplace transformation using this form. Okay, let's look at example here. So we have the function ft cos omega t ut. Right. The Laplace transformation of cos omega t ut is simply s over s squared plus omega squared. So this is taken from the table, Laplace transform pairs. Okay. So if we have cos omega t, the t itself is shifted by a, and then the ut also shifted by a, then we will have the Laplace transformation as this. As right. First, you need to put this. Okay. You need to put this at the front, and then do the Laplace transformation of the ft, which is fs. Right. So that is the difference. So make sure that the shift is appear on both t, and it is similar. Alright, so this is actually the same example in the previous video, in which we use the equation to get the Laplace transformation of the ft. So let's look at what is the result, or what is the answer if we use table. Right, so if you recall, we have function ut, which is 1 ut, right? 1 ut. Okay, 1 ut. So the Laplace transformation of 1 ut, if you use the equation, right? You recall the equation ft e negative ft dt, right? From 0 to infinity. This is the equation for Laplace transformation. Then try to solve this, and finally we get 1 over s. So this is the table taken from table, 1 over s. So if you have, let's say the question perform Laplace transformation of ft, which is 3 ut. So the fs is basically 3 over s. Alright, so you have 1 here, you have 1 here. If you have 3 here, you have 3 here. It's simple as that. Next is the same example as before, right? So we have ft equals to e negative at ut, right? Now remember that ut means that the function only exists above 0t, 0t and above, right? So meaning that the exponential function in negative time, it did not exist, right? So only appear this way. So in that case, we can use the Laplace transformation. Use the Laplace transformation of one direction, a single direction, from 0 to infinity. We'll try to solve this, and then finally this is the answer, right? So actually this is referring to the table. Okay, we put this in the table. Exponential negative at is equals to 1 over s plus a. So let's say the question asks you how to perform Laplace transformation of 3 exponential negative 4t, right? So means that 3 over s plus 4, right? Or another example, 10 exponential 4t. So this is positive 4, right? So now is 10 as negative 4. Alright, so if the value is negative a, then you write it as positive a. If it's positive a, put it as negative a. So it's the reverse of that. Right. Another example. Right. Cos omega t. Right. So this is as in the previous video. This whole thing here. So the answer is s over s squared plus omega squared. So this is from the table. We have this from the table. Right. So let's say the question asks you how to do Laplace transformation of, let's say, tan cos omega t. So it is simply as the answer is tan s, right? It's tan s over s squared plus s squared, right? Or let's say ft equals tan cos 5t, right? Write that again, tan cos 5t. So now 5 is instead of w, it is 5. So now the answer for fs is s over tan s over s squared. What was it? 5 squared. Right. So if the omega is other value, let's say 5, then replace w with 5, omega with 5, right? Right, let's look at example here. So we have yt. So it can be yt, ft, xt, doesn't matter as long as it is in time domain, right? So let's say we have yt equals to 5 cos 2t minus 1 ut. Alright, how to perform Laplace transformation of this function? Right, first of all, let's look at the problem here. So we have what we have here is what we're trying to solve here is this cos 2t minus 1. Alright, so cos 2t minus 1. So because the 5 here, we can bring it outside. Okay, it's just a constant value. It will not affect, will not be considered in the Laplace transformation. Okay, just put it outside here. Alright, so what we have here is cos omega t plus theta. Right, this is cos omega t plus theta. Do we have this in the table? Let's look. Yes. See here, cos omega t plus theta is actually the Laplace transformation of cos omega t plus theta is, right, s cos theta minus omega sin theta over s squared plus omega squared. Right. So we have this. The answer is already given in the table. So this is the Laplace transformation of cos omega t plus theta. So now we just have to replace the value. So in this case, omega is 2, right? So we will change this with 2 and this with 2, right? And then plus theta is actually negative 1, right? So plus theta plus theta is negative 1, negative 1, negative 1, right? Right. And then this is the Laplace transformation of the yt. actually if this is yt, then your answer is capital Ys. Okay, so this should be capital Ys, which is not really a big problem, right? Then this is your answer, right? Or you can simplify, change the make it less complicated, alright, in which sine -1 is also equals to sine 1, and then cos 1, cos -1 equals to cos 1, it's like this, right? Okay, next let's look at this example. Zt, which is 4 exponential 2t minus exponential negative t cos t. Alright, so here what we should do is we try to solve this one by one. Okay, try to solve this individually, right? So for 4e 2t, or 4 exponential 2t, alright, formula plus transformation of this is simply for 1 over s minus 2, right? So this is should be straightforward. Now the next one is exponential negative t cos t, right? Is this available in the table? Let's look. Alright, so frequency shift, right? The one. Let's look at it. Exponential negative t cos t, exponential negative t cos t, exponential negative t cos t. Okay, exponential negative at cos, exponential negative at cos omega t, which is s plus a over s plus a squared plus omega, right? You can use this transformation table. So exponential negative t cos t is basically s plus 1 s plus 1 plus 1 squared, right? Because this omega is now 1 and cos omega t also 1, right? This is omega, this is also omega. In this case omega is 1, so we have 1 here. Alright, so then you can solve these two, then subtract, and then you will get this answer. So that is how you use the Laplace transformation table. Okay, instead of using the equation, you can just simply solve the transformation using the table.